talk about dynamic transitions in non-equilibrium work fluctuations of linear diffusion systems.
Yeah, I also thank the organizers for giving me a chance to talk in this beautiful conference. What I'm going to talk about today is somewhat subtle, but still very interesting and maybe surprising dynamic transitions we found in the tail of work PDF in a very simple linear diffusion systems. So these are my collaborators, Jae-dong No and Cheol-Lang Kwon, who were here in the first week, already left, and we have few publications on this, and we are still working on because we do not have a full understanding of these dynamic transitions. Okay, I'll start with the simple, the fluctuation theorems. We have a system and reservoir, external agents. We have a heat and work exchanged between them. And if you prepare the system in some initial distribution and evolve over time t, then we now all know some integrated quantity satisfies so-called integral fluctuation theorem. One example is this total entry production during that time span, or also the dissipated work, which is known as the Jasinski identity, and many others. But this integral fluctuation theorem sometimes sensitive this initial condition, initial distribution of the system. But first one doesn't matter of any kind of initial condition. It works for any initial condition. But the second, Jasinski equality, only works for the equilibrium initial distribution. You all know that. From there, you can, show the thermodynamic second law very easily. And we also know something about so-called detailed fluctuation theorem, which is about the distribution function of this integrated quantity. So ratio between these two probability satisfy this simple equation. And the denominator, this p tilde, is for the reverse process, usually. But if you do not have any time-dependent protocol, then this reverse process is basically equivalent to the forward process. So in that case, this detailed fluctuation gives you the information about relation between this rare event region and frequent event region. So they are related in a very simple way. That's we learned from the fluctuation theorem over the last 20 years. It's useful, sometimes useful to think about the generating function, which is defined in this way. So basically exponentiated minus lambda R average is defined in this way. And this detailed fluctuation theorem can be written in terms of this symmetry of generating function, which is known as Galois-Cohen symmetry. So if we are, in this work, we are focusing on this tail probability, the tail region. So if you know the tail, then you know also the bulk. So first, this is a simple thing. So we focus on the tail region. This tail usually decays exponentially in non-equilibrium process. So that means this way. So when R is very big, then this guy is exponential decay. This decay, if you put it here, then you can easily see that this generating function has a singularity at some specific value of lambda, which represents this exponential decay slope. And this symmetry going to tell you about, you have also, the singularity in the other region. Okay, this is the starting point. Basically, what I'm interested in this tail region, I'm looking at this A, so exponential slope, by studying the generating function singularities for the very simple system. So this is my one-page summary of our result, is this. We consider very simple linear diffusion system, basically colloidal particle suspending on a fluid, but you have some kind of torque. So you have some non-equilibrium force, non-conservative force. Then That's all. So we have no time-dependent protocol and trying to watch what is the probability distribution of dissipated work, especially in the tail part, as a function of time. Of course, reverse process same as forward process, and also there is no free energy difference between the first beginning and the end. So basically, dissipated work is total work in this case. Okay. Let's think about t equals 0. You start. You do not do anything, any work, so obviously must be the this distribution function has a delta function at the origin. And you expect as time goes by, you are doing some work, so average work is moving. But you have also fluctuation develops, and time goes on, you have more developing, and probably going into some asymptotic, the asymptotic shape in the time goes infinity limit. That's the usual we can think. Yes? Yeah, I'm going to talk about a particular model, very simple model. So that's I called simple linear diffusion system. But surprisingly, what he found is this tail shape, as time goes by, it's not smoothly changing, but sharply changing through we call dynamic locking, unlocking type transitions. What I mean by that is this is time axis. Up to some time, the earlier time, this is the tail, this tail part of this distribution function, which you can expect from the beginning. We have this exponential part, but this coefficient is changing in time. Obviously, at the beginning, this lambda 0 must be infinity because this is delta function and decaying. But after some time t, basically, this lambda 0 is locked to some constant and not moving at all. We call this region is region 1 and this is region 2. So this is the dynamic transition I'm referring to. This is happening. And more surprisingly, sometimes we are finding a sequence of dynamic transitions, which is, well, you are in the region 1 and go to the region 2. That means your lambda 0 is changing and stuck, changing and stuck, changing and stuck infinitely many times, all depending on specific details of our model. Okay, this is the thing I'm trying to talk today. So go to the model. Brownian dynamics is very simple dynamics and white noise, but this is all high dimensional. And you go to the overdamped limit. So forget about this inertia term. And you divide this force into the two terms, is conservative term and non-conservative terms. You need non-conservative terms to generate the non-equilibrium work. And the work done by this conservative force is basically only changing your internal energy. So this is the one I'm focusing on. This is work done by the non-conservative force. To solve analytically, you're only thinking about the linear force. So this is basically multivariate Ornstein-Uhlenbeck process. So you can solve everything analytically. So for this so-called force matrix is composed of these two, conservative part and non-conservative part. This is symmetric. Conservative part requires this symmetricity of this force matrix, and energy only given by this way. A non-conservative part is not symmetric. So this guy is going to give you the non-equilibrium steady state in time goes by, usually having a rotational current in the system. Here we can calculate everything exactly. The simple examples I'm talking about is this is particle dynamics trapped in a harmonic potential because this is a linear problem driven by the swirling force. for example, in 2 dimensions, like here. This is conservative part, matrix is symmetric, but you see that this guy and that guy is different. That means anisotropic harmonic potential. And this non-conservative part is antisymmetric. Basically, this is torque. And all other examples, this can also apply to so-called Brownian gyrator, studied in, already 10 years ago, to model the nano heat engine. They're also looking for the anisotropic harmonic potential, but instead of using the swirling force, they are using the 2 different temperature reservoirs to make this rotation. Also similar, there are many other examples of that, rotational molecular motor system, and even global climate system, which can be described by linear diffusion equations. Also, you can think about underdamped case is also molecular refrigerator, which studied 10 years ago. This is basically, using this velocity as a state variable, but they're all linear, so basically belong to this kind of guy. And even you can go to a time-dependent harmonic potential and all that. But in my point of view, most of these work focus either on a fluctuation theorem point of view or the long-term limit, so looking for the only large deviation function. And even if when you look at the transient behavior, they did not find anything interesting. But here, what I'm going to report is we found a very interesting transient behavior. That's the whole thing. Okay, we first set the gamma gamma and D is all identity, without loss of generality. The temperature is basically 1. So this is a simple model. And white noise. What you're going to do is basically you're doing the Onsaga-Metchlef type formulation. Most of you know about this. So final PDF is just the initial integration of initial PDF and all the path integral. This so-called Lagrangian is given by this guy, x dot plus fx, and square, because we are assuming the noise is Gaussian. This Lagrangian is, of course, quadratic only. So everything is Gaussian. Integral, you can do everything analytically. So what you're expecting is final PDF must follow this kind of Gaussian. Only thing you have to calculate this kernel, matrix A, which is time dependent, with some initial condition, which is equilibrium. And easily you can find this differential equation A dot equals this, the right-hand side. That is this guy is satisfying this equation. The only thing you have to do is solve this equation. At the beginning, it looks difficult, but because this is nonlinear term, but standard way is you take the inverse of this guy with this form, inverse, dynamics of inverse is basically following the linear. So linear equation you can solve. Then inverse and put it back, and this is all you can calculate. We are interested in the generating function. The calculation of generating function is not much different. This guy is basically written in this way. Basically same path integral, but you have to calculate this guy. So you put this e to the minus lambda w on the top and integral over the final point 2, because this is an average. The only thing you have to do is this calculation. So almost the same, except you have a modified Lagrangian. And work is basically this. This is non-conservative force times velocity and integral, that's the work. So basically modified Lagrangian is this. You just put it here. This final Lagrangian is also quadratic. So you put it here, then you adding these two guys, and arrange the things, the complete square and all that, then the similar equation you can end up with, instead of this guy, very similar. Of course, this, in order to distinguish this guy, that guy, I put the tilde here. And during this exact square process, this f is changed to the f tilde, and you have inhomogeneous term coming up.
That in the second but last line.
Second but last line.
That one, that integral e to the power minus lambda w is outside the time integral.
Inside of time integral.
No.
No. Oh, sorry. So actually, this one is here. So thank you. So only thing, what you have to do is solve this guy. It is a little bit more difficult because of this inhomogeneous term, and all this modified F matrix is a little bit complicated, but it's not much matter. It's just constant matrix. But it can be easily solved by so-called shifting, or I call the translation. So you put the A tilde equals steady state solution plus something else. Then you can get rid of this inhomogeneous term. Then you end up with this kind of guy. Then you invert. Then equation becomes linear. So you can solve it. Solution is complicated, but basically, and even in 2D, we are able to find the explicit form, but it looks horrible. I'm not going to present here. But basically, what you are interested in this guy, this is a bunch of Gaussian integrals of these kernels. So if you take the Gaussian integral, then what you end up is determinant of this kernel. Yeah? So this guy, if you integral, then your determinant coming out. So this is basically product of all the determinants from time 0 to the t. That's the only thing. So if you take the log of that, log g, and log is sum of log of determinant. Log of determinant is basically trace. So you can go to this is basically becoming an integral, but you have a last term, bounded term left, which is the last guy, at time t. If you look at whole this guy, I'm looking for the singularity, which determines the tail part, tail shape of the distribution function. All these guys, whatever you do, this is, you could not find any kind of singularity here. Because A is kernel, and a kernel should not diverge. Integral, trace, integral, nothing coming out. However, here, if determinant hitting 0, then this log 0 makes this generating function diverge. So only thing I have to look at is this, how this determinant behaves as a function of time. Okay, so before I'm going to report the result of this guy in our simple system, just imagine this kind of thing you found. This is the determinant of this guy versus time, and this is constant lambda line. So you fix constant, you fix lambda, and time goes by. And lambda is very small. You're expecting this determinant is maybe positive. It decays, but stay all the way to the positive region as time goes by. But if you going larger than lambda and lambda c, then usually going through this meet the x-axis, then becoming negative. So in between, there is a critical line. at lambda c, so this is all the way. But if lambda is a little bit larger than lambda c, then this guy sometime later hit the 0. Okay, this is the one typical graph you can see from this analysis. So what this figure means, if you look at some fixed time and going over like that, then you're going to see the lambda, the maximum lambda you can see is the lambda value of this lambda, constant lambda curve. Because lambda is larger than this guy, constant lambda line is going down, it's already hit the infinity. So finite value must be, lambda must be allowed only. Lambda is less than this lambda. This lambda I call lambda 0t. Of course, this, for fixed t, this lambda 0 is function of t. So if you nearby lambda equal lambda 0t, so I'm looking at this curve and another lambda curve. At fixed time, if you go up, then this determinant should be like a linear, going to 0 at lambda equal lambda 0t. What this means? This means you put this is linear, and you have minus 1/2 in front, log, so this is square root singularity in the generating function. So basically you are expecting this. Generating function diverges at lambda 0, and this, the other part is given by the Galois Cohen symmetry. It's like that. If something like that happens, you know, I already said that if generating function diverges at some value of lambda, it sets the tail part of this distributional work. Here, this guy must be same as this guy. So I know from the singularity, I know what is this. And this prefactor coming out reflects this square of the singularity. If you increase time, now you go to here, then here, for example, then this lambda 0 must be this guy. And this is lambda is, if you go up, then lambda is smaller. So if you go further and further, then lambda 0t should decrease. So should decrease, and time goes to infinity. Then because of this existence of this critical line, you never, this lambda 0t is approaching lambda equal lambda c. Okay, so this you are expecting lambda 0t decreasing from the beginning, from the infinity to down, and slowly going to approach the lambda c value. That's the usual thing you can expect. This is, I call type 1. But imagine something this happened. So this determinant is not monotonically decreasing. Something like you have a curvature like that. And you can think of the same thing. Small lambda, I call this red curve is lambda c, which touch this x-axis. And if your lambda is larger than lambda c, then only this curve exists, because here is already this log minus going to give you generating function is infinity. So if Tc is smaller than T1, you are expecting the same thing. So linear and quadratic, and lambda 0 is changing as time goes by, lambda 0 is decreasing. But if you look at this guy, lambda equal lambda c is the maximum value allowed. You are not going to have any value of this guy. And if you go to further, the same curve. This is the only curve allowed. Not only curve, this is a curve allowed with maximum lambda. So that's the type 2. So if in this case, if you look at this T2 value, the first guy, you're going to see that this guy, this G is non-zero. So when you approach lambda c, this is constant. It's not infinity, but after lambda is lambda c, it must be diverging. So this is this continuous divergence. Here is I already said, this lambda c is not changing at all as a function time goes by. So this guy is not changing. So this is I call type 2. So if you see this kind of thing, then something is happening. So this is the simplest case I present. You have this force matrix, conservative. So basically this is anisotropic harmonic potential. And this is the torque. I took the Q equals 0.3. And this is the thing. This y-axis is basically determinant of this guy. And x-axis is time. And if small y, this anisotropy, small y is big, but still not very big. What you're going to see, this guy is basically linearly crossing, monotonically crossing. There is some oscillation, but it's not important. So you are expecting this in this case, everywhere as time goes by, you are in the type 1. But if you look at this guy, the last one, this is y is strong, 0.8. You're going to see this critical curve. If you see the critical curve, then there is a dynamic transition, 1 to 2, from this point already. And in between, much more complex thing is going on. And even we can identify exactly at the critical y value. At the critical y value is also interesting. This critical curve touching this x-axis infinitely many times with the exact periodicity. So from here, what you learn is this. This is the y-axis, y-controlled anisotropy. And this is time. I said the Q is 0.3. As I said before, y is small. Nothing is changing. You are sitting in phase 1. So like that, so lambda 0 is changing smoothly. But if you go to large y, then you have a second phase. So for example, you fix the y value and changing time, you are not going to see nothing. This is actually this lambda 0. This is the curve, corresponding curve. Lambda 0 versus time. Lambda 0 is decreasing and decreasing, some oscillation, but decreasing and all the way down. And if you look at here, y is a little bigger, then you have a transition. That means this curve. So lambda is changing very fast, but constant after this critical time. Here is something strange going on. This curve is going down and locked, unlocked, locked, and infinitely many times going on. And this is the critical line I talked about. At the critical line, we can calculate everything analytically very well. Okay, this is Q is 0.3. If you change Q, what is happening? This is rather complicated curve. Is this lowest line is when Q approaches 0. It's not exactly 0. When Q equals 0, then there is no work. But Q is approaching, still you are doing some work. And this is the phase diagram. And if you increase Q, then you're going to go up and up. So whole thing is now we found mathematically there is a dynamic transitions. But what is the origin of this dynamic transition. Well, still we do not have a full understanding, but we have some, the hint from this diagram. You see, where this line and that line, if there is a transition from 1 to 2, so this line is not much depending on y value or q. They're all starting from the same point. It's not exactly the same, but approximately the same. This is order 1. So how order 1 coming out? Because we already set, the gamma and d equal 1. So relaxation time scale in equilibrium is basically order 1. So this reason is you are starting from some equilibrium. You turn on your torque, and this guy is trying to change. And at the beginning is some kind of equilibrium relaxation to some other. That's I think is what is happening in here. But if it happens to change it to phase 2, this relaxation, it doesn't matter, only depending on whether y is small or big. Y is small, no transition, smoothly changing. Y is big, you're changing something to the different phase. What y represents, y is basically anisotropy of the enharmonic potential. So if it is really enharmonic, then the decay mode is quite slow because you have a very weak potential in one direction. So decay is very slow. And also what you learn here, so that is something doing. The other thing is, even though there are a lot of the oscillation structure of this phase boundary, in average, phase 2 existence of phase 2 is shrinking as Q increasing. So what Q is basically torque. So what that means is if torque is too big compared to your anisotropy of enharmonic potential, then they are not, this guy does not see the anisotropy very well. Then it is harmonic potential, no anisotropy. That's basically belong to y equals 0. Y equals 0 is anisotropy. So you're basically torque is dominant and anisotropy is not there. So this region stay alive when torque and this basically rotational mode by torque and decaying mode by anisotropy is working together, somehow making this phase. However, that's not, I'm just saying, the very, how can I say, naive way of saying is not really good understanding, because this transition is really sharp transition, a locking transition. It's like Shapiro steps you've seen in the Joseph junction array. But still, we are trying to map this problem to other problems, which are much more better understood, but still we are not successful. But this one is also, similar to some well-studied model, well-studied case, tilted washboard potential. Well, if this radial component is not very much fluctuating, then basically this is oscillation mode. So that's if you're thinking about only the oscillation angle, that's basically tilted washboard potential. But this one is interesting. This can be solved. PDF can be solved exactly, but I'm not sure whether one can solve PDF for the work for this system because this is highly nonlinear. But in this system, it is very similar, but linear in high dimension, so you can solve. There are many things we thinking about the initial contingent equilibrium, whether this kind of thing is stay alive in different initial condition, or about the heat distribution. And if you go to underdamped, time dependent potential, what's going to happening? We're still thinking about it, but basically, main missing point is why this sharping locking transition is happening in this very simple model. Your distribution function tail is slowly changing, and at some point it's stuck there. Then to slowly changing and stuck there. This kind of jerky motion. This is happening in the tail, but you know from the detailed fluctuation theorem, this tail part is related to the frequent event region. So it's basically bulk region. So even in bulk, something is happening similar related to this transition. That's what we are thinking. Yeah, this is it. Thank you very much.
There are questions or comments? Yes, Udo?
I'm slightly confused. Perhaps you can clarify. I thought in these linear problems, the work distribution is Gaussian.
Yeah. No. That's when work is a simple, then for example, harmonic potential and moving with a constant velocity, that's the only thing you have a work distribution Gaussian. If harmonic potential with breathing mode, of course, already is exponential. And this torque, of course, is going to make you the...
So you're saying that torque is the torque is like in the other case, as in the other case I had a breathing mode.
Yeah. Well, in general, the Gaussian nature of Gaussianity of this work distribution function only works, I think, when you have moving this harmonic potential with a constant velocity. That's the only case.
Okay, I would have to look back to our work 10 years ago with Thomas Speck.
Yeah.
I think we looked at time-dependent linear work distributions in any dimension, and at that time we found a Gaussian distribution.
No. Actually, I know that paper. Maybe you can discuss later.
Yes.
You talked about that prefactor at the time.
Does your locking transition depend on the initial distribution that you choose?
Well, in this case, we are only working on the equilibrium distribution.
So
we did not really go into some other initial distribution, but I'm not sure about the delta function distribution. But in general, I think this is happening. But we actually did not carry out any calculation.
Okay. It would be interesting, I think, in the zero range process, for instance, if you just take two sides, you can interpret it as a random walk in two dimensions in some potential. And there, for not this problem, but for a related problem, we found discontinuity in the current distribution, which might be related to this.
Okay, that may be a very good example to map to.
Okay, Sanjeev?
This variables.
Yeah.
Just, I think that's the reason probably.
Well, because,
Somewhere in the beginning, I guess. Yeah.
So work is basically non-conservative force times, the velocity, work rate. So x dot times non-conservative force.
Yeah, maybe. Yeah.
Oops. But force, non-conservative force is linear.
Yeah.
This one.
But you have two x's, so that work is.
This is x dot.
Yeah, so it's
velocity.
Yeah, so that's why Paul is non-Gaussian.
So this is all quadratic.
Yeah.
So everything is quadratic, but that Gaussian nature is going this guy. But if you integral out, then you're going to have a singularity. So you have a.
So the expression of this, you have this e power something to the power W, right? Like when the asymptotic tail of the work distribution.
Yeah.
So that's actually really asymptotic, right? Like in the limit W going to infinity.
Not time goes infinity.
But also
the
W really
value
going to
is
infinity, right?
Yeah.
Not any finite W will not have this form. It will probably go to
finite. Any small time, still you have a probability to have a very big work. So
I mean, like what I mean is that the asymptotic W can be like square root of W square plus 1, which is asymptotically mod W.
the bulk, not the tail part, in the middle part is of course Gaussian, but you're going to have this tail is exponential, and I'm looking at Gaussian is not much. This tail part has a very strange behavior, and as I said, from the detailed fluctuation theorem, this tail part is related to the center part. So even though we cannot see very well in the bulk part, there something is going on in the bulk part too. That's what I'm thinking.
Okay. No other questions? No comments? Okay, then let's thank Hynggyu and the other speakers of this morning again.